Hello and welcome back to Calculus 2. Welcome back to Sequences, part 2. We're going to take a look at some rules and properties about sequences. Last class, we defined the sequence as the ordered list of numbers. And ordering was done through the natural set n. And you were supposed to be able to obtain terms as you plug in 1, 2, 3, 4 or 0, 1, 2, 3, 4, depending which way it's defined. We said that the notation is an, followed by either the list of numbers separated by commas or a formula which would generate that list. Your skill needs to be there to transform either the formula into list of numbers or list of numbers into the formula. Right, so going back and forth. We also said some sequences are recursive, which means that the new term, to generate the new term, it depends on the previous term, or two terms, or a couple of previous terms. Talked about the Zeno's paradox of the archer that shoots the arrow, right? And we talked about there's always a halfway missing till you hit the target, and we used it to explain what we call the limit test for sequences. And we see that sequences either converge or diverge depending on the answer you get in the limit. If you get a number, which includes 0 obviously, it converges to that number. If you get any of the infinities, positive or negative, the sequence is divergent. But we also at the end encountered this particular sequence, which was also divergent, because at infinity, limit does not exist. These numbers do not settle down to a particular value, but they don't even go to infinity. So this is still divergent case, but divergent in the sense that not going to infinity, but divergent in the sense that it doesn't actually converge to a single value. So if I am to write in that limit as n goes to infinity of -1 to the n, the limit simply does not exist, and we claim divergence. Because in order to claim convergence, limit has to be equal to a number. Now, I did talk briefly about this, and we will see it again very soon. So we'll leave it there. The goal for today, few theorems and rules and stuff, so we can deal with these things. So all of the limit laws that apply to numbers apply to sequences as well. Actually, before I do number 1, let limit of an converge to a. So it's a convergent sequence that converges to a. And let the limit of bn converges to capital B. So both of these are convergent sequences because they have a finite number, a and b, whatever those numbers are. So that will be the limit of the sequence, which means converges to that number. Now, with that in mind, if you have two convergent sequences like that, then these 4 rules apply. Limit of an plus bn as n goes to infinity, and will always go to infinity for the next 2 chapters. So limit as n goes to infinity is just a plus b. So you can deal with them separately and then add the results, or you can combine 2 sequences into the big sequence and then deal with that. Number 2 is the multiplication. Oh, the first one also assumes the subtraction as well. I missed that, sorry. So plus minus. Now we're moving on to the next one. Limit n goes to infinity of some constant c multiplying an, that spells can over there, is you can kick the constant outside, just deal with the limit of an, so it becomes ca. Number 3, limit of an bn is ab. which is very convenient. So no product rule, quotient rule, or any of those. I mean, those are for derivatives anyway, but the limits are so nice because you can actually do the product and quotient. And finally, number 4, if you divide them, you just divide the answers. So an divided by bn is just going to be a over b, provided b is not 0. So cool rules, and you can work of these. So I did mention yesterday and sometime before that L'Hopital's rule is going to be your friend. So please make sure I believe that's 4.7, make sure you know it back and forth so you can actually do problems in this chapter. I will give you an example of it. Say an is given as 4x cubed for n cubed plus 2n minus 6 divided by n cubed minus 1. So say this is a problem and you want to check whether it converges or diverges. Now you can, plug in n equals to 0, n equals to 1, n equals to 2, come up with this, but that's not going to tell you anything. You have to do the limit test. That's the only way to check. If you are looking for convergence or divergence of a sequence, you must use limit test. So you are supposed to take the limit n goes to infinity of 4n cubed plus 2n minus 6 divided by n cubed minus 1. And when you plug infinity in, you get infinity over infinity, which is the indeterminate form, which we study as a part of L'Hopital rule. L'Hopital rule is applied when you have 0 divided by 0 or infinity divided by infinity. And the way L'Hopital rule works is you take independent derivatives of numerator and denominator, so it's not a quotient rule, independent derivatives of numerator and denominator, and then try to work out the problem again. So by L'Hopital rule, you have to put L'H because these functions are not going to be the same at all. You didn't do even the quotient rule, right? But their result is the same, which is great. So now we take the derivative on top, we get 12n squared plus 2, and on the bottom we get 3n squared. So now when you check infinity, you still have infinity over infinity, so you do L'Hopital again. And you get limit n goes to infinity, derivative on top, 24n, derivative on the bottom, 6n. Well, now it's simple. It just reduces down to 4, because 24 divided by 6 is 4, and n cancels n, so we are good to go. There are other methods by which you can solve this particular problem but But then there are some problems that are absolute horror, and if you don't know logarithmic way to solve these in conjunction with L'Hopital rule, well then hell breaks loose. So here is the sequence an equals n raised to the 1 over n. As soon as you see a variable in a base n exponent, the only way you can take them apart is if you apply ln on both sides. So if I have y, let's say y equals limit n goes to infinity of n to 1 over n, you might try and gamble with this and try to make an educated guess or try to be way too smart with it. Chances are you're going to definitely get it wrong, because you have infinity raised to 0. Infinity is trying to make everything infinite 0, and the exponent should make everything 1. So which one is it? Is it infinity or is it 1, right? If I have infinity raised to 0, that's what I have here. N is going to infinity, this n is going to infinity, but 1 over infinity is 0. So now, which one wins? Or maybe they meet somewhere at, let's say, 3/4, whatever. So which one wins? This is why we have to do calculation. You cannot look at it and say, oh, anything raised to the 0 is 1, because it's not. So we have to be very careful about that. The way to solve this problem is to get rid of the exponent, and the only way you can do that is if you ln both sides. Now this is a method that you will learn, that you learned in the past. You learned this in 4.7 for those last cases, 1 to infinity and infinity to 0 and 0 raised to 0. You had those cases there, and they were all solved through ln both sides. This should not be new to you, but I'll review it anyway, just in case. So we have ln y on the right. On the left, we're going to swap limit and ln, because ln is increasing function. I have 1 over n jump in front of ln, just have ln of n. So we use the formula that peels off the exponent and pushes it in front of ln. So now, you technically have that ln y is equal to the limit n goes to infinity of ln n divided by n. And since both of these are increasing functions, you have infinity over infinity, and at this point it's a L'Hopital's rule, so you can take these derivatives. You still have limit n goes to infinity, and now when you take the derivative of ln, you get 1 over n, and over here derivative of this is equal to 1. Okay, so now this is equal to 0, right? It's equal to 0. And if you now write that ln y is equal to 0, you will e both sides to get rid of ln, and you get that y is equal to e to the 0, which is 1. But remember what y was. Y was the limit that you were looking for. So the limit of n to the 1 over n as n goes to infinity, which is the limit test, is equal to 1. Who would say that infinity raised to the 0 is 1? Well, in this case it is. Can we change it? Yes, we can. We can make it go to different values. I want to take a look and verify that this limit is 1. Let's say your limit skills are not there yet, and you are, pulling your hair out on over the weekend trying to figure this stuff out. All you need to do is to go to your favorite graphing tool. I'll use Desmos. So what I'm going to do is just graph x raised to 1 divided by x, and and as you can see, as you zoom out, it's kind of terrible that it zooms out this way, but you see that it peaks, doesn't really reach 2, right? Remember, this is the limit as it goes to infinity, so I don't care what's happening x equals 0, x equals 1, x equals 2. I care what's happening at x equals infinity, going to infinity. So I'm not looking at the front end of this graph. I'm looking at the tail end, the back, right? So I'm looking at what's happening as n's go to infinity. So now, if I keep moving this function, you can see that it keeps getting closer and closer and closer to 1. The red line is keep approaching. And I'm already, each one of these, 113, that's n equals 113, n equals 114, n equals 115, and you can see this red line approaching the black line, which is where the level of 1 is. Go to infinity, limit is 1. Awesome. So you can check these. You can check these by simply graphing the function. Now, when I said this, you have to be very careful because sequences and series, that's the part of discrete mathematics. So input value of 1.5 doesn't exist. What you are getting is a series of dots, right? There is a value, and then there is nothing, then there's a value, there's nothing. While when you graph a function, you always have, if it's continuous, obviously, you always have something going on, right? For any value of x you pick, there is a value of y if the function is continuous. Now, these graphs are series of dots. So if I am to, let's just talk about graph real quick. Graph of a sequence. Say you have a sequence, an is equal to 1 over n. And in the blue corner, f of x equals 1 over x. So the creature on the right is the creature that you know. And you can carefully figure out where the points are that you want to use to graph it. So let's say if this point over here is 1, 1, that's 2, that's a half, that's 3, that's a third, that's a 4, that's a quarter, and we know what this thing looks like because it's 1 over x graph. And it will have another branch over here. So this is the mathematics that you guys know. Now, if you just focus on the dots that I put, that is the graph of your sequence. So an, and another part is that there are no negative values. Remember that the counting starts either at 0 or at 1. So we can't start 1 over n at 0 because it will be 1 over 0. So we have to start at 1, and for 1, you just get a dot on the 1, level 1. At 2, you have a dot. At 3, you have a dot. At 4, you have a dot. And you can see these dots approaching the n axis, natural numbers, much the same way as 1 over x approaches as it goes to infinity. They are the same, they have the same shape, except the one for the sequences is not filled in with a continuous line. So you can compute 1 over x for 1.5. You cannot compute sequence at 1.5. It's computing at 1, then at 2, then at 3, which is the discrete chunks, right? And because they're discrete chunks, that's why it forms the basis for computer science. Because in computer science, what you have is the discrete type of environment, where ultimately everything boils down to current is flowing, current is not flowing, on, off, 1, 0, right? Everything boils down to that, and you can just tick to have one of the two happen. So this chapter is the sole reason why computer science is taking this course. And that's that. So that's the graphs. And now I need to find terminology for sequences to learn about increasing, non-increasing, and bounded, and all of these kind of things. And I believe after that, I think we are done. Geometric I'm going to cover after the break. There's the theorem. Oh, growth rates are here. Okay, we'll have to do that as well. So there's quite a few things left, so let's work on them one at a time. So terminology. So these are the important words that you need to know what they mean, because a lot of problems will be using these words. And obviously, if you don't know what they mean, then you can't do a lot. So, number one, AN is increasing if AN plus 1 is larger than AN. So this simply says that the next term, which is plus 1, right, is bigger than the previous term. And now here comes the confusing part. AN is non-decreasing if AN plus 1 is larger or equal than AN. Negative language on this one. Non-decreasing. Well, it's a very clever way of saying that it is increasing and constant at the same time. You see the top one, number 1, the number coming up next absolutely must be larger than the previous term. The number 2 allows possibility for you to have the same value. So for number 1, you can write as an example, 1, 2, 3, 4, 5, and so on. So that's number 1. Because as you go from one term to the next term is always strictly larger than the previous term. Now, if you take a look at the example for number 2, you can go 1, 2, and then maybe have, how about this? 1, 2, 2, 3, 3, 3, ... So, you look at that. Is it increasing? Yes, it's increasing. But at the same time, there are chunks that are constant. So, some values are the same, which is why we have to have equal, and then increase. So the best way to put 2 of these words into a single word is to say non-decreasing. Because the only thing that the sequence is not doing is going down. Sequence can go up, sequence can go down, or can stay flat. Those are the 3 options, right? Up, so grow, or decay, or stay constant. So the fastest way it's better than including 2 words to just exclude the one that it's not. That's kind of fun. Number 3, we are going to talk about decreasing. So AN is decreasing if the next term is strictly smaller, and then again you have the non-increasing, same idea. If AN plus 1 less than or equal than AN. Number 5, AN is monotonic. So maybe I should just underline important words. Increasing, non-decreasing, decreasing, non-increasing, monotonic. Those are the words we have. So sequence AN is monotonic if it's either non-decreasing or non-increasing. If it is either non-decreasing or non-increasing. I'll let you sort that out in your head when you read it again. And bounded. AN is bounded if there is a number m. So the word bounded is important here. So AN is bounded if there is a number m such that AN is less than m for all n. You can do less than equal to, it's fine. So this one is bounded from above. And you can create one of these easily. You can just say, let me draw the graph. Let me do the graph for inverse tangent of x. Inverse tangent of x is bounded by between two horizontal asymptotes. So the sequence that it generates will also be bounded by those same values, same location. So if you have AN to be inverse tangent of n, then you can use the function as a guide. So you draw the light curve. So let me first put the asymptotes at top pi over 2 and then the bottom negative pi over 2. So the dots will arrange themselves in the pattern to follow the graph. Now we do not have a negative side, so we'll get rid of all the negative values. I just wanted to draw them all so I can shoot the inverse tangent line. Now obviously we don't need any of those. We only need the dots on the right hand side because our sequences start either at 0 or higher, right? Like 1. So there they are, the points. And we say that AN is bounded from above and the reason is it's bounded by pi over 2. So AN is bounded from above by pi over 2. Because these dots will never cross pi over 2. They climb up quickly and then they just hang around that one because it's going to infinity and you just really can't pierce through the vertical asymptotes. But well. Okay, so that's that part. So bounded, let me just write, AN is bounded from above by pi over 2 and below by negative pi over 2. So the cool theorem, a bounded monotonic sequence always converges. So a bounded monotonic sequence always converges. Did my Ooh. Okay, what is my mistake? In the black writing over there, the words I provided as the answer. What's my mistake? It's only bounded from above, right? I don't know why I added this. It's not supposed to be there. It's just bounded from the top. The function is bounded from below as well because it goes to negative pi over 2. So we don't need that stuff. I'm going to erase it so it's not in the notes confusing people. And if you are watching the stream, I made a mistake because you guys made me make a mistake. All right, fine. The most useful thing of everything here is growth rate of functions. Holy nightmare, this thing is powerful. I'm even going to put the red title on this. Growth rate or rates of functions. No, growth rate of functions. Because there is only one growth rate at which one function progresses. As a figure of speech, you heard many times someone says, oh, it grows exponentially, meaning it grows really fast. Well, that's great, but we don't just have exponential functions. We have logarithmic functions and polynomials and radical with square roots. Trig is not going to be in here because trig is a joke. When you have a sine or a cosine function, what do? They go, yes, they're periodic. They go to the top to be 1, go to the bottom to be -1, and they just stay in their range. They're kind of boring, right? So there's no growth rate in there because as soon as one function reaches y equals to 2, sine and cosine can never reach y equals to 2 because they're bounded at 1. So it's not that fun to talk about growth rate of sine and cosine. But here are other functions that we can talk about. And we will start this list with the lowest, slowest rising function amongst all, and that is ln raised to some exponent. So let's say ln of n raised to some exponent q. Now, you might say, well, hold on. If I use q equals 1,000,000, it is going to grow fast. Again, I don't care about your finite numbers. They're completely irrelevant. I don't care how big of a number you choose. It is going to be insignificant in comparison to infinity. Right? You can sit there and just push 1 and then push 0 and just hold your finger until you develop whatever and die. And the number that you have, even if you were able to hold it somehow for years and people were, feeding the food into you and all of that kind of stuff, your number is still nothing in comparison to infinity, right? And you might have years worth of adding zeros after the 1. Just there is no finite time in which you can sit and write out or construct a number that is going to rival infinity. It's very simple, right? So no matter which q you pose here to be the exponent, it's not going to do anything. Now, that is going to grow slower than a polynomial function. You see that? So imagine you have your ln of n raised to 1,000,000. Well, then you can use the same million to raise n to 1,000,000 over there, and one on the right is going to win. It's going to be a larger number. So these are carefully placed where they go. Now, this is going to grow slower than when you combine these two, which makes sense because the multiplication of the two produces the larger number than each individual one. And that is going to grow slower than if you had polynomial increased by whatever other exponent. This is bizarre, guys. You have the exponent here, right? N to the p, you have n to the p. And you say, well, how about if it is just p to the 1, and I have this q a million? That's okay. This term will be winning for some finite time, and eventually this one is going to overtake. And once it overtakes, it's gone. This one will never be able to compete. So, if you multiply two polynomials, you will always get a faster growing function than if you multiply a polynomial into ln. Here is the exponential, b to the n. Beats ln's, beats polynomials, right? And there's your exponential right there. Are we done? No. There is something that is called factorial. And factorial is going to grow faster than exponential. And then finally, over here, at the end of this list, is our good friend, which I call the boss function, n to the n. Now, those of you that are not familiar with this, I can't do it because my voice is shot. Usually, I make a joke where I scream n, and I just say, this is not, and then I scream, it is a factorial, so you just read it as n factorial. There's no reason to scream. N factorial is just multiplication of all integers leading up to your number, which is your n. So 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. And we will deal with these factorials a lot in this chapter. We are going to learn some properties of factorials. We don't need them today, so I'm not going to go through properties and other things. You just need to know what it is, because now what I'm going to do is I'm going to create a chart of values. I gotta move this. Bye-bye. Because I want to create a chart of values so you guys can observe how these values win over time. I'm not going to deal with ln's, don't need to waste time with that one. I'm going to use n, 2n, n squared, 2 to the n, n factorial, n to the n. Now, values for n are simply going to be 1, 2, 3, 4, and let's say 5. So 2n will double each one of these numbers. And we see that 2n grows faster because by the time that the first column got to 5 as a value, the second column got to 10. Now, we are claiming that n squared is even faster than 2n. Well, compute it. N squared, 1 squared is 1. And you will say, it's losing. Hold on. 2 squared is 4. See, it caught up. And then you have 3 squared, which is 9, and that is beating a 6. 4 squared is 16, that's beating 8. And then 5 squared is 25, which is beating 10. So you see that having a linear and then having a squared function grows faster. And then you get to exponential. So 2 to the n is 2. 2 to the 1 is 2. And 2 squared, 2 to the 2, 2 squared is 4. And then 2 to the 3 is 8. It's not doing too hot, right, in comparison to the other one. Because the next one is 2 to the 4, and that's 16. So it's like, starts good, and then the other one catches up, and then it goes worse, and then it catches up, and so on. But now, 2 to the 5 is 32. This is where it takes off. This is what I say. When you are dealing with these things, you do not want to look what's happening for the finite amount of terms in the beginning. Because, as you can see, the n, 2 to the n, exponential one, right, was losing right here. It was losing to the n squared. And then it caught up in the next one. And from this point on, it will be winning big time. Because the next row is 36 versus 64. So it immediately wins. Now here are the n factorials. 1, lame. 2, not that much. 6, it's losing, right? But now, 4 factorial is going to be 24. And as you can see, it started winning over there. And the next one we calculated 120. You know what the next number is? 120 times 6. 720 is the next number. Compare that to 6 and 12, right? The exponential function, 2 to the 6, is going to be 64. And the factorial is going to be at 720. I did some research with number systems, and I had to work out this number. Obviously, I coded the computer to do it for me. Came up in Microsoft Word with 1-inch margins everywhere and a font 12. Came up with a number that was 27 pages long of digits, where the last 10 pages were all zeros. So just imagine a number that is 27 pages, font 12, right? Holy nightmare. And then 121, this was, you'll see it was Pascal's triangle, right? 121 factorial had 11 pages of numbers. 11 pages. Last 4 or 5 pages were all zeros, because you end up multiplying, right, the numbers, because up to 121 you have 10, you have 20, you have 30, 40, 50, right? So there it keeps accumulating zeros at the end. And then every time you have 5 times 2, and you have a lot of those, that also creates 10. So, wow, it's a lot of zeros. But those are zeros added after numbers, so these are huge numbers, right? Factorial grows much faster than exponential function, making the other functions completely irrelevant in their existence, right? But we have one more, the one that I called the boss. And the boss, yeah, that's the one that it starts sluggish. 1 raised to the 1 is 1. And 2 squared is 4. And these are the only 2 values where n to the n is kind of, it's okay. The next one is 3 cubed. That's 27. Look at the third row, right? You're talking, everything is like 6, 8, 9. This guy's at 27. What's 4 to the 4? 4 to the 4? 256, right? Oh, it's 10 times bigger than the factorial, right? And it's 16 times bigger than the exponential. This is 5 to 5, like a lot. It's really a lot. 5 to the 5, you have 25 squared. So 5 to the 5 can be written as 5 squared times 5 squared times 5. That's 25 squared times 5. 25 squared is 625 times 5. Now, if you are lazy to multiply, what you can do is you can multiply by 10 and divide by 2, which is much better way than multiplying by 5. Right? Because it's easier to divide by 2, take a half, than to multiply by 5. But if you want to multiply and you don't want to use a calculator, 6 times 5 is 30 and 2 zeros. 20 times 5 is so you have 3,000 on that one. 20 times 5 is 100, and 5 times 5 is 25, so 3125. If you have a calculator available, take a look what 7 to the 7 is on the line 7, just to get an idea of how quickly this function goes, which is why I call it the boss. So I hope you understand. And the question is, why do we want to know this? Well, it helps a great deal when we are looking for limits like this. Limit n goes to infinity, because they all do in a limit test. And let's say you have 3 to the n plus 7 divided by n to the n. Your argument is that the boss function in the denominator grows much quicker than the exponential in the numerator. Therefore, the limit is 0. Limit n goes to infinity of 3n factorial divided by, let's pick on exponential again, 4n plus 10. Well, now the top grows faster, so the answer is infinity. So over here I'll say denominator faster, and on the second one, numerator is faster. So it helps us when we have these functions that are not of a kind, and solving this limit algebraically would be a living nightmare. We can take a look at growth rate of functions, because if the functions are not of the same kind, you have only two possible answers, either 0 or infinity. No other answers are available if they are not a match. If you're mixing polynomial with exponential, exponential with factorial, factorial with polynomial, the boss function with factorial, doesn't matter. If you are matching different columns from this chart or different ones from this list, the answers can only be 0 or infinity. Now, what I'm going to write is not mathematically correct to write, which I'm going to use the quotes, but it's very easy to remember when you deal with these limits. So, quote, limit n goes to infinity of fast over slow is infinity. Again, terrible, bad notation, but it helps you remember this and solve limits quickly when you can, when it has this. Limit n goes to infinity of slow over fast is going to give you 0. So those are the two possibilities that you guys have. And if you know the ordering, then you can use this, and you don't have to calculate a lot of limits. You can just say, oh, by growth rate of functions, boom, done. And you move along. So it doesn't apply, does not apply in every problem, but when it does apply, great. That's it. Bye.